in the meantime, let me get there's two, okay, so there's going to be two parts to it. Hang on, let me get the dynamics book up first. That's a good question. Let's check it. I need to, okay, it looks like it's good. Do what now? Is it echoing? How about that? Is that a little bit? I think I could probably do that too to make it. We've got two chapters that go here, but I'll just say chapter 12 is the only in class, and the chapter, which I think it's 16, is only going to be the take home. And so I don't want to review it till I have the actually take home made. I just didn't scan it into a PDF and do it quite yet, but I'll scan it and put it on the blackboard, and then on Friday we'll talk about it. So all I want to address is this right now. So what I'm going to do is go section by section and tell you what I'm going to target. So the first part, let me get rid of that. Okay, hang on. The first part, he starts off with a general description of velocity, acceleration, things like that. And he starts in this coordinate system with S, one-dimensional. So he has all of these, and he does all this, and this is great. He does it for constant acceleration for all these terms, puts a big, nice blue box around it. Also, let me tell you this. I'm going to go to this. I'm going to go back. At the very end of the chapter, at the end of every chapter, he has this thing on chapter review. I'm going to take, oh, that's only one page. I thought it was 2 pages. There's got to be more. There's only 1 page here? Well, is it for 13? Oh, it is. Okay. All right. Okay, now I'm in there. So I say they have to have that other set of equations in there. Okay, so chapter 12, those pages. Okay, so all these pages. There we go. Okay, and I need also, okay, these two, this set right here. So all of these pages I'm going to print out, and I'll even print them in color so you can see the difference. And they'll be probably not stapled to the back of the test, but also just to the side. So you won't have to peel the back off and flip it around. So you can do what you want with them, but I'm just going to take those pages. That's it. So if you look on there and see, it might be worth a few minutes looking at it and trying to see what's what there. I think this section will be important. That little part right here, you'll want to know that. And we'll talk about that in a second. If I give you anything on this, I'm not going to make you go find the curvature, which is not there. Wait, I could have swore I just saw the curvature defined. I guess I didn't. I guess maybe that was done. So I'm not going to make you find the curvature. That's just basically going in and doing derivatives. So with that, what are the types of problems? The first section is with the integration and stuff. I'm not going to basically do any of that, but I am going to do the section called erratic motion, which is not necessarily erratic. It can still be smooth. But I can give you a case in point of something that is I could pretty much guarantee it's been on the test every time for the last 5 years that I've done it. So there's no particular reason for me not to do it now. Oh, and that is, let's say you just take a graph that has the velocity as a function of time. And I don't want to overcomplicate things, so I'll probably just use straight lines. Oops, that's supposed to be a flat line. something like this, and says it goes down to here. And then instead of you coming in and, writing the graph, 0 is going to be positive, oops, and then it's going to be negative. So instead of doing that, which it's okay to do that for homework, but for a test, I don't want to be staring at these graphs. They'll make me blind. So the way I generally do it is I'll come in, give you that graph and tell you, this is 10 and this is 15 and this is 5 seconds and 10. And I'm not going to do silly numbers like 10.2 or something like that. That's just a waste of time, and say this is 30 seconds. And then I may come in and list the whole thing. I'll probably do them in 2 parts, one on one page, one on the other, and say something like the acceleration at 3 seconds is equal to, and you just figure it out. So at 3 seconds, you just do rise over run, 10 over 5 or 2. And that's pretty much it. And then I might do another one, acceleration at 7 seconds, and just do several things on the graph so that I can tell whether you know how to interpret it here, 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 and here. Now, if I do something this by mistake where I say something like, that's supposed to be 15 seconds. So let's say I came in and gave you a plot, looks very much like this. And then I said the acceleration of 15, what would you put? Because you got a slope that could be like this, it could be anything from here. Yeah, there's several answers that are kind of true. Now, if I did acceleration at 14.99, and I could do that, it's slightly to the left, it's slightly to the right. You can go in MATLAB and monkey around and make this plot and try to take the derivative. And what it does is it takes the derivative to the left, the derivative to the right, and then puts it right and takes the average of them. So it's claiming that's the right answer. But, I don't know. I will not probably try to do that. If I do that by accident, you've got a wide range that you could input, that you could put that would be the correct answer. Then the next key is position. Position's a little bit easier, because if you look at it, this is the case. And I'm sorry. You were looking at me thinking, oh, this is a new way of doing it. So something like this. So all you're doing is integrating this to get your S over here. So all you're doing is at 5, you're just looking to find the area of this triangle back here. At S equal 10, you're looking for the area of everything to the left. That's basically everything to the left. So if you look at this first one, what is it? 10 times 5, 5 times 10, and, half of that. And I think that's 25. I think that's 25. 5 times 10 is 50. Half that's 25. Then you got the area right here. If you wanted to be like one of those type of people, that the area there is what? 5, 10, it's 50. So here is 25 plus that 50. So this one's 25, that one's 50. So you just march to the right, or wherever the point is, you look back to your left and you find out what all the areas were before you got there. And that's pretty much it. On these erratic motions, I'm not going to put 2 or 3 or 4 of them. There's just going to be one picture. It always is velocity, because that way I can force you to do differentiation and then force you to do a little integration. If you understand that concept, and you'd be surprised people who most people that kind of attended class and sort of did a few of the homework and did stuff like that, they pretty much get 100 on that. But there's a block of people that come in, low percentage, maybe 10%, that'll just blow the thing to pieces. They'll put in the wrong answer for like 9 out of 10 of them or something. So, it happens. And so all you got, and it's an easy thing to do. It's not that bad. So then going to the next thing. Okay, so you get past erratic motion. That'll be just one problem with several different questions. So you go on down. Da, 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 da. Here, I think I'm going to use the page down button. It gets there faster. Now you could do this curvilinear motion, and it's all great, but the focal point here is these things, the projectiles. This equation is in that little back part. In other words, what you need for this is really you just need that one, and you need okay. Well, you need let me redo it. You need this one, and you need that one. Actually, you don't need that one. Here, hang on. Erase that. You don't need that one. You need this one. So I'll give you those two. You don't have to memorize any of that stuff. And then, there's 2 or 3 different things you could do. I don't necessarily feel like wanting to go through the hassle of grading something that says, oh, I shot a cannon and it did like this, boom, and landed down there. But so I'm probably not going to do something like that, but I might do something where somebody threw something off of the roof, and you're trying to hit somebody down there, how far did it go? So I may ask something like a distance there, say this is 10 foot back, and I may also ask how high it is. So I could ask how high does it go? Usually, and I think I'll go ahead and do this, is put the coordinate system right there on the object that's being kicked or shot or whatever. Because if you do that, you have at Vy naught T minus GT squared over 2. If you do that, if you put the coordinate system there, this term and that term go away. That makes it easier. And you'll get an angle, and or it might be, 3, 4, 5, things like that. You'll either get the angle and the velocity, or 3, 4, 5, or something like that in the velocity. Then you're just working out what this is, what that is. You'll have to look at your unit. So if this is in meters, you keep up with that. G is equal to 9.81 for meters second squared, or 32.2 for feet second squared. So it's going to be one of those two. You should know that but if you forget do the stress of the test, just let me know. I will probably write it on the page anyway. And by the way, this is the way I'm going to do this test. Before I've done these tests where you circle the dot and I run it through the grader and stuff, I'm going to just make this one by hand. And what I'll do is I'll ask you, and I'll ask you, what is D? What is D? And then what I'll do is put a box. So make sure you put it in the box, So first I can find it. Then when I find it, if I go and find it and it's right, and I look at the stuff and it says, oh, it looks pretty reasonable, I won't look at the work. But if you put in something like a weird number, then it gives me a chance to go back and give you partial credit on the stuff that led up to the box. So whatever you do, you probably want to do, if you just write the number down and it's wrong and I don't have any partial credit to give, that's not good. So yeah, show your work, and I'll give you some pages, there'll be empty pages there. I'll have probably a drawing, and then maybe the next page I might say, find this and fill it in the box on the next page. So you could use that page and the next page to work it. Although it shouldn't be too long. Then you got, so you got that. Okay, and here they go. Okay, a ton of those problems. Okay, so normal and tangential component. I'm not going to ask anything on that. Most of the problems that he gives in the homework, it's the issues come up right here. So he makes you find that a lot. And there's nothing wrong with that. It's just, I don't want to, that's just using your calculator to find the derivatives. Don't want to have to do that. However, when I get to this next, but I won't make it ridiculous. And you saw these were in the book on that review page. Although these are blue, so I might copy these and put them on the problem itself so that you don't have to flip around over there. So I'll try to do that when I can think of it. When I don't think of it, there'll be that page. When I think of it and I'm giving you something that has to use these equations, I'll try to put it on the page. Because I don't remember those things. I can derive them, but I can't remember them. I can remember the velocity one. I can't remember the acceleration one. Just not a problem. Now there are hard problems here, some that take a long time, some that don't. And let me give you a couple of cases that are not as bad as you think. So if I came in and I said, and of course I'm going to have to do a reasonable job of drawing it. So I may actually make MATLAB draw the curve or whatever. By the way, those were supposed to be straight lines. So say you had a straight line, somebody said, okay, here's R, and it did something like this. And say, here's an easy one, okay? So let's say 3, I don't know, t squared? Good enough for me. And say theta is, what do I want to do? How about just t? Then these you could probably pretty much do. Well, first I could do this, okay? If that's t, then theta dot is what? 1, right? What's theta double dot? Nothing. So then if I list them up here, okay, let me see. 6t and then 6. So if I make you do derivatives, that's the level I'm going to put it at. Now, I could make you also do another derivative that's fun to do is, e to the 2t, something like that. What's that one? What's r dot there? 2e to the 2t, right? Is that right? And then 4e to the 2t, something. Those are the type things, if I gave you something, I would give you to do. I don't know which one's easier, but they're all there. And then somebody could ask, well, when t is equal to, I don't know, what's the velocity? And then if I ask you that, probably I'll ask you like this. Velocity equals to some number times e. I'm sorry, I just said e, but I meant to say r. I meant to say u plus e theta. Now the thing is if you look back here, oh, I moved past that page. Okay. So here I just asked for the velocity that time. So if you look at it, that's all you're looking to find. So you just have to find r and r theta. So if you stuck in, okay, let's make my life easier here. Let's do it for 1 second so I can do this problem. So that'd be 3, this would be 6, this would be 6, this would be, what I say, 1, this would be 1, this would be 0. So if I'm looking to put in UR is R dot goes here, R theta dot goes here. Okay, R dot. Oh, mistake. Okay, sorry about that. R dot is 6, 6. R times theta dot, 3 times 1, and you're done. And then the other one, okay, so if you think about it, you go down, I think it's the next page. Uh-oh. Here it is. This is the one that's harder for me to remember. I can't ever remember that thing. But, okay, so it's, all it is, okay, so let's see if I can, okay, here. Since I can't remember it, and I'm not going to remember it, so here, I'll just copy it, put it on the page somewhere. Oh, man. Man, that wind yesterday got in my nose. I've been sneezing ever since. Here, get rid of that thing. I'll move this thing up so I can make it all fit on the same page. Oh, wrong way. So if I ask you the acceleration, that's just something times UR. That's the acceleration in the R direction. Acceleration is the theta. Okay, if you do that, R double dot. Okay, so let me fill out the AR over to the side. R double dot, 6 minus R, 3, theta dot squared, 1 squared. I think I get 3. Is that right? And then A theta, R, dot 6, theta dot 1. 12. Looks like I got 12. So if you can do things like that with either something like this one, okay, if you were doing this one, let's say we did that one for a second. I would accept sticking the E in there. In other words, if I said R equals to, E, okay, almost T, R dot equals to 2E to the minus, 2T, R double dot equal to 4, E to the 2T. And then say I said T is equal to 1, then this would be E2, 2E2, 4E2. So you can just leave it as E. In that way, your answers would just have some E's in them. Does that make sense? I mean, I can grade that fine. If you want to type it out on your calculator, that's fine. But if you do and you monkey it up by pushing the wrong button, then I got to grade what you put in the box. So make it easier for me and just leave it as E. Make it easier for you too. So if I do the E, just put the E in there. If you want to. I mean, if you want to type it out, was it 2.73 something, 13 or something? It's up to you. Okay, so then when we get done with that, so that's it. I mean, that's all you have to do. Okay, go. And then he has a whole pile of problems. Let me shrink it way down so I can go faster. So he's got a whole pile of problems in that section. And then the ropes. Now, okay, after the ropes is this relative stuff, like this. I'm not putting that on the end class because that's going to be heavily used in the take-home portion. So the only other thing is ropes. I'm just going to give you a rope thing. Just a simple, I mean, I'll draw it by hand and I'll do the best I can. But I know I bought myself this circle template. I use it now. I was showing my daughter yesterday. You just put it in there. You can make all these different size circles. And I'm going to make it on the engineering page and then Xerox it. And so there'll be the thing, you'll see it when you Xerox the engineering pages, those little lines that come down the engineering page, they go away. So you'll see the border and you'll see the problem statement. So it's just going to be a copy like that. So if I do something, oops. Okay, I'm going to draw some, let's just say, I mean, you can make up anything. You make up your own. It doesn't matter. Here, I don't know. Let's do that. Okay, so I made something stupid and ridiculous. It is pretty stupid. So let's connect this thing to, all right, well, this is really stupid if I do this because here, what do you think is going to happen with that one? So, okay, so now I say I move this with velocity equal to 2. What's the velocity of this thing? Oh, I got to connect this to the wall. Well, if the weight is properly distributed right there, you should be okay. Do what now? It's it. Yeah. So let's just pick a spot. Okay. The other thing is I didn't do something else here. Here. This is a bad drawing. I'll do better than this. I mean, but you can make any set you want. You stare at it a minute. You're like, oh, okay, I get it. So here, here I'll make a datum that goes out to this point. Say, here, I guess I'll call it A, SA, and then I'll make this thing go down to here, SB. So I'll call this B, say. So this pulley is connected to right here, which is connected. So these are basically on the rope. So if you really wanted that, if you wanted to do that color coding thing, that doesn't change. What about this? Does this change? Yeah, so those don't change. This one doesn't change. And this part doesn't change. And this part doesn't change. So if you go in, you start counting them. I get 1, 2, 3 S. So I'm sorry, SB. And then I get plus 1. Why did I write a 1? I usually don't do that. SA plus all the red deltas. So all the red deltas, those are your links. And so, you know, if you look at it, you take your derivative, you get 0 equals to SA dot plus 3SB dot. Did I say 3? Yeah, I said 3. Man, that projector box is hot. Okay, what did I say? I said that was 2, right? So that's 2. So then the direction down to here, okay, so if you move this over, you look at it over there, you get minus 2 is equal to 3SB, or SB is equal to minus 2/3. However, that's pointing down as plus, so that means it is going up at 2/3. Or did I say 2/3? Yeah, 2/3. So, you know, something like that, just a simple, I don't know, you can draw many different things. They all the same thing. You could just, I mean, I've done this before just for kicks. I mean, it's kind of stupid, but I could do a big, sometimes you get out of control. Here, you got something like that. And then it takes a few more minutes to draw this, though. Okay, so then just connect this to the wall. I guess I got to do this. I got to do that. Ah, missed. Got to do that. And then I guess I could do this. Pull it with a motor. So, I mean, you can put as many of those as you want. And then start identifying the dead links. Or, okay, I didn't finish this, did I? Okay. This is connected to the wall. This is connected to the wall. And that's connected to the wall. For that matter, so is that one. And that has 2 supports, so it doesn't pull off to the side. So you got that, you got that, you got this, you got that one, you got that one, and technically I could say this one too. Oh, and this one. And then I could start saying the things that change. I could basically go out here, call this SA, go from here down, call it SB. Now I got 1, 2, 3, 4, 5, 6, 7, 8. So if I did that, you know, say this was 8. Oh, say, here. You usually don't say that. You usually say this. Velocity is equal to 8. So for the moving 8, the other one's moving up 1. So that's it. I mean, how many pages is that? So I started there. No, wait a minute. I started here. So the plot, you know what? Let's do it this way. So you got the erratic motion one. Then you got a projectile one. Then you got a moderately simple one with something that, you know, is so easy to take the derivative. You'd be wasting your time trying to put it in the calculator. You know, I would think the easiest thing is like a t to the third, t squared. If I want to make sure there's an acceleration component, I'm going to have to pick like theta is equal to like t squared or something. So I'm going to have to put, e to the t. Well, I could do that too. That would, you know. So, I mean, I'll have to put something like that. So if I want to see that term, the key is if I want to see that term show up, and I might want it to show up. In the case I've got here, I don't have it showing up. So just something that the derivative could be easy to do. And then a rope problem, which, so how many is that? 1, 2, 3, 4. That's enough. That's enough. And then the rest, and that's it. I mean, I'm just going to draw them by hand. I'm not going to try to make them. This one will have all flats. There's not going to be a thing like this. So I'm not doing that. This will be just, it could be kicking uphill or kicking downhill. Say somebody wanted to kick it. Somebody's down there and wanted to kick the ball on the roof. You know, I used to do that when I was a kid all the time. Although you were doing it not on a flat roof. I mean, I would get, like all other kids, you'd get in the driveway and the roof's sitting here and it's like this. So you'd throw it up there and it'd come back and you'd catch it as it came off the roof, you know. That's pretty common. Although sometimes I'd throw it and I'd have to go to the backyard because then it'd end up running down the backyard. I had, my parents had, you know, nowadays people, you go out and see these houses with all these weird roofs that are all weird pitches. First thing that I always think when I see it is what a waste of money, because I grew up building houses and my dad did that for 50, 60 years. More like close to 70. But anyway, when we'd get out there, I mean, I don't know how many times we'd get out there and people would stand around, look at the drawings because he drew them too. So they'd stand up there, wow, I wonder what Mr. George did with that thing. Oh gosh, you know, it'd take them 30 minutes to figure out how to do 2 rafters at a funny angle. And I'd stand out there, and I was at 15 years old, and I was like, come on, you know, what are we standing here for? It's 5 guys standing trying to figure out what to do, tell the 6th guy what to do up there. He's standing up there with a hammer. Pretty soon, you know, you'd notice how many hours were wasted trying to figure out complex pitches. And then the other thing, you throw it and it ends up over here or over there, all these weird pitches, and everybody thinks that's the way to do a roof. And I keep thinking, first of all, it costs you a lot more money, a lot more than you think to put that pitch on there. Second thing is, every time you do a complex pitch, you got a possibility of a leak. Because I had a roofer, I called him one time. I said, I got a leak. He just did my roof. I got a leak. Well, you know, all roofs leak. And I said, no, I'm only concerned about mine, you know, and you did the thing. And he never came back out. Should have sued him. But anyway, then, you know, yeah, so many things that people do in building houses that are a total waste of time these days. Just do a pitch like this. Like it starts here, it goes down the roof like this, you know. And the other thing, so while we're on this, it just annoys me. Why build a house, have this giant pitch like this? I mean, huge. And then you put yourself in here. Here you are standing, feeling like the thing's going to collapse on you. When you put 2 more people standing on top of each other in the attic. I mean, so your attic space is twice the space. Have you ever seen that? You're driving down, oh, wow, look at the pitch of that roof, you know, and you're looking at it and you're thinking, God, what a waste of space. At least, you know, make it so, you know, the outside, when you go outside, you look out and you see there's nothing over the top of you.
Are we going to do a sign-in bonus today?
Oh, yeah. Here, what's the pitch of this roof? pitch. Just 3/4. Or you could do 4/3. It's the same. Some people will say 3/4. What?
Why is MechLab 1 a 2-hour class that lasts 4 hours?
The same reason this roof is pitched the way it is. It's like 3/4 of a fifth. It's a good thing that you're not going and getting 1 hour credit for a 16-hour lab. Now that would be, so always look at these things like it could be worse. Someone, I could go to lab and someone beats me with a hammer. That would be worse. You're trying to have me put logic on stuff that I don't know how to do. Yeah, why? Still, I'm confused by that one. Yeah, 4/3, 3/5. By the way, I'm not going to look at the number anyway. I'm just going to put you. Oh, make sure your name is on the top.